Alright, welcome back. This lecture's a bummer, isn't it? I mean, there's just so much bad news here. And this whole idea of climate stabilization, it's a great idea, a great scientific concept, but the truth of the matter is, it probably doesn't even work on human timescales. Like on the scales that society can actually make any kind of plans on. I mean, the truth of the matter is, there's so many things that we don't really know that much about how it works. For example, we really don't know that well, or can't model that well, how vegetation will be changing due to climate and producing climate feedbacks. We're going to actually talk more about that in just a few minutes. We don't really know very much more about how the methane ices that are trapped in the ocean are going to eventually end up in the atmosphere and create a feedback. But we'll talk more about that in just a little bit. And we really don't know how stable, like, the major ice sheets in Antarctica are, and how likely it is that we're going to be melting those and causing sea level increases and ice albedo feedbacks and oh man. Can you see that guy just beating his head against the desk? At some point, you're killing me, Dr. Shruggy. It's all just a mess. Can't we learn about something happier? Aren't there any... You guys are environmental science majors. There's no happy stories in environmental science, right? Are there ever problems that we had information, we did something smart about it, and we solved a problem because I could really use that today? And the answer is, kinda, yeah. There is one happy story. The whole story of the ozone hole and halocarbons. Now, this course is not about the ozone hole and halocarbons, but I think from classes like Intro to Meteorology and stuff like that, you guys know this story, that we got ourselves into a whole lot of trouble with regard to the ozone layer. We made useful materials like halocarbons, and those materials are wonderful, but they also have this really serious problem of they also, caused the ozone hole. And this diagram is too small for you to see here, but that's a visualization of the ozone hole since 1979. And you can see at first it was growing really fast, and now if anything it's stable, maybe even getting a little smaller. And that's a happy thing, because we used good science and international cooperation and good diplomacy, and we came up with an international treaty called the Monero Protocol that banned the kinds of halocarbons that were causing the ozone hole. And it's a happy story, right? We're happy. Environmental science classes often pitch this as a good example of a success story in environmental science, but is it really that? Another spin on this is that this is not actually a happy story. Another interpretation we could have of this whole story is that we came really close to a disaster. And we just got really lucky that the right politicians with the right diplomatic skills, and frankly, the corporations had alternative materials and were willing to not fight replacement of halocarbons because they had companies like DuPont Chemical and so on, and Dow Chemical and so on, already had alternatives to those halocarbons. We always sell this as being such a happy story. It's not really a happy story in some interpretations. Another thing is to say, holy cow, it really could have gone either way. We just sort of had the right people at the right time to make it all happen. And the same could be true of climate change here. Maybe all our estimates about the amount of fossil fuels we're going to be burning, what if we're just radically wrong about that? What if our assumptions here are wrong? I mean, new technology for extracting fossil fuels could be a game changer. Fracking has been a game changer. No one could have guessed we'd have as much shale oil and methane 10, 15, 20 years ago. Those were all pipe dreams. Oh no. We changed everything with just a new piece of technology. Or tar sands, right? The process to get our petroleum products out of tar sands was known 20 years ago, but not economically viable. Now it is. Even with very low oil prices, it makes sense, makes some measure of sense anyway, to do tar sands. What if we're just radically wrong about this? Or what if the public turns on it? I mean, the Fukushima nuclear reactor accident of a few years ago pretty much ended all attempts to get Japan off of fossil fuels through nuclear power. You might love nuclear power, you might hate nuclear power. Nuclear power is a complicated issue in and of itself, but at least it's green. Okay? It does not result in fossil fuels in the atmosphere. And a big industrial nation has decided they hate it, namely Japan. That was previously very bullish on such things. Oh. Suddenly, they're building things like coal pipe. Can you imagine? A big, industrialized, powerful, rich, well-educated country like Japan is out there burning coal again. It changes so fast. Oh no. The truth of it is, all these projections that we have of the climate, you know, A1, A2, B1, B2, or all those RCP pathways, all of these projections, both in the short term and the long term, just don't have any mechanism in them to adjust for abrupt changes that could happen. The arrival of disruptive technologies that could make it vastly cheaper and more effective to get fossil fuels, or, in a happier way, make it easier to get rid of them, to switch to solar, or to switch to wind, or to switch to whatever. None of these scenarios take any way into scenario things like war that could totally change our availability of fossil fuels, or our consumption of fossil fuels, or whatever. None of them take into account natural disasters. None of them take into account big economic changes that could change the demand for such things. They talk about slow changes. Gradual demographic changes in Asia, or the spread of technologies, of slow technological incremental changes. Nothing abrupt is in any of these models. Oh no. And frankly, the kind of changes I have listed there, they're all societal type things that could just make our forecast useless. This isn't a class about society and climate change, okay? Let's talk about things that could go wrong in the climate system that could completely mess up our forecasts. That's called abrupt climate change. Abrupt climate change is kind of a fun, fashionable, exciting thing in the sense of like climate science. It's interesting to think about ways in the past climate changed fast, like comet impacts or the Younger Dryas or other abrupt climate changes that have happened in the past. When we talk about abrupt climate changes, we're talking about a large-scale change in the climate system that takes place over a few decades or less. Sometimes we're talking literally like a bad day, like a comet impact, and persists, or at least is anticipated to be able to persist for at least a few decades, and causes substantial disruptions in human and natural systems. Okay, so we're talking about a big, maybe even global scale event that changes the climate, takes no more than a decade or so to actually happen, and sets up basically permanent, irreversible type changes. Comet impacts, collapses of ocean circulation patterns, stratovolcanoes, supervolcanoes, all are possible ideas of what we're talking about here, okay? They could set up abrupt climate changes. And one of the ones that is most plausible, at least in the relatively short outcome here, is a change to the so-called Atlantic Meridional Overturning Current, or the sometimes called AMOC, sometimes called MOC. This is an ocean current system that is in the North Atlantic that is driven by temperature differences across the Atlantic Ocean and salinity differences across the ocean. There is a production of, well, fresh water comes off of Greenland in the form of melting ice. Yeah, I don't want to get, this isn't an oceanography class, let's not get into the business of figuring out. There's an ocean current here that is being driven. It's the Atlantic Meridional Overturning Current. It is a big part of the regional climate of North America and Europe in particular. It's part of the reason why Europe is so warm despite being so far north. I mean, look on a map sometime as to how far north, say, Denmark is, and then compare that to like a similar latitude in, say, Asia or in North America, and you're like, wow, how does it have such a warm climate? It's partially because of this meridional overturning current, and it is largely driven by temperature and salinity differences, the production of sea ice, the production of icebergs, the production, all that ties into how this current works, and there's strong reason to believe that in a warmer world, this current could collapse, and we would no longer have that transport of warm water from the equatorial Atlantic and the tropical Atlantic up towards Northern Europe, up towards Britain, etc. And ocean models seem to indicate that that could happen. Models show that there is a threshold beyond which a certain amount of change in the distribution of production of ice and fresh water and salty water and all that kind of stuff in the North Atlantic, the circulation no longer exists. That's actually kind of a fun thing because it really makes a very abrupt change of climate. And I should steer you toward an interesting book. It's kind of just a pulpy thing. I don't know if you're familiar with the science fiction writer Kim Stanley Robinson, but Kim Stanley Robinson's 40 Signs of Rain is an interesting book that came out about 10 years ago, in which the North Atlantic meridional overturning current collapses. And it effectively throws the climate system into a new younger dryas. And we no longer are transporting warm water toward Europe, and Europe's climate becomes very cold. And it's fascinating. I'm not sure I exactly recommend the book, because the book itself, I think it's loosely framed around a murder at the National Science Foundation building. I mean, it's kind of pulpy, but it's fun. And it just reminded me of that. But apparently there's some temperature beyond which, if the global mean temperature doesn't, if it hits that, the meridional overturning current ends. Now, we don't know exactly where that threshold is, because lots of different ocean models exist, and they have very different ideas as to where that global mean temperature is, at which point that abrupt climate change happens. But based on the variable models and so on in the literature, it remains very likely that this circulation is going to weaken throughout the 21st century relative to its pre-industrial levels. And there's a wide range. I mean, notice how it says the best estimate is 11%, but the range of estimates is from 1% to 24%. That's a big range of estimates. And notice how, like in the higher emission scenarios, the amount it weakens goes from 12 to 52. These are huge ranges in the amount of weakening of this current. But there is not very much reason at the present time in current models to think that there is a lot of confidence here that this is going to result in a collapse of that current. It might, but there is not much confidence that the models are doing that right now. Again, remembering that term confidence was something we defined way back in Module 1. Therefore, as a consequence, the scientific consensus is that while we need to be understanding what the Atlantic meridional overturning current is doing, it is actually not very likely to collapse between now and the end of the 21st century, but collapse of that current beyond the 21st century is certainly something that cannot be excluded at the present time, because we are getting to temperatures by that time at which that current system starts to collapse. And then after that, our climate models are no good. We don't really know, we have no way of testing that the models even know how to do this. Okay? It isn't like there are past examples of this, that we have buoys and stuff like that, and we have measured and we can see if our model can simulate it. That's an abrupt climate change that we can't really figure out what would happen beyond that. Here's another possible abrupt climate change. How about the collapse of ice sheets in West Antarctica or in Greenland? I have a map here of Antarctica. In case you didn't know, Antarctica has kind of two halves to it that correspond pretty well to the Western Hemisphere and the Eastern Hemisphere. And the West Antarctic part of it is a problem.